resources via the operating system. Handling common file formats such as CSV and XML. Working with dates and times. Automating applications and accessing their APIs. Using third-party modules to extend automation beyond the standard library capabilities. WROX.com downloads for this chapter. For this chapter, the WROX.com code downloads are found at www.rox.com/go/www.rox.com/go/python projects on the Download Code tab. The code is in the Chapter 2 download, called chapter2.zip, and individually named according to the names throughout the chapter. Often, you may find yourself undertaking tasks that involve many repetitive operations. To combat this repetition of work, it may be possible to write a macro to automate those operations within a single application, but if the operations span several applications, macros are rarely effective. For example, if you back up and archive a large multimedia web application, you may have to deal with content produced by one or more media tools, code from an IDE, and probably some database files too. Instead of macros, you need an external programming tool to drive each application, or utility, to perform its part of the whole. Python is well suited to this kind of orchestration role. 2. 48 Chapter 2 Scripting with Python. In this chapter you learn how to use Python modules to check user settings, as well as directory and file access levels, set up the correct environment for an operation, and launch and control external programs from your script. You also discover how Python modules help you access data in common file formats, how to handle dates and times, and, finally, how to directly access the low-level programming interfaces of external applications using the very powerful Types module and, for Windows, the Pywin32 package. What is scripting? Scripting is a term that means different things to different people, so it's important to clarify up front what it means when you see it in this chapter. It means coordinating the actions of other programs or applications to perform a task such as bulk file printing, or an automated workflow, such as adding a new user. You could be using operating system utilities or large general-purpose packages, like an OFFIC productivity suite. Think of the way that a script in a play tells the actors what to say, where to stand, and when to enter or exit the stage. That's what Python scripting does. It coordinates the behavior of other programs. System-specific issues. By the nature of the discussion, much of this chapter's content is operating system specific. Some modules try to be portable across operating systems, whereas others support only a subset of operations on some systems. Others come with dedicated modules that work only on that platform. If you find an example that doesn't seem to work for you, make sure it is not for a different operating system. Whenever possible, we try to point out which modules are specific to a particular system. Also, in the Try It Out sections, the output is often quite specific to the user and operating system, so don't expect to get exactly the same results as shown. For example, when checking user details, you should see your own username, not the one shown. Accessing the operating system. Most of the tasks that a typical programmer needs to undertake using the operating system, for example, collecting user information or navigating the file system, can be done in a generic way using Python's standard library of modules. Recall that modules are reusable pieces of code that can be shared across multiple programs. The key modules have been written in such a way that the peculiarities of individual operating system behaviors have been hidden behind a higher-level set of objects and operations. The modules that you consider in this section are OS/path, PWD, glob, shootil, and subprocess. The material here focuses on how to use these modules in common scenarios. It does not try to cover every possible permutation or available option. Accessing the operating system. 49. Obtaining information about users and their computer. One of the first things you can do when exploring the OS modules is to find out what they can tell you about users. Specifically, you can find out the user's ID, login name, and some of his default settings. Like most new things in Python, the best way to get familiar is via the interactive prompt, so fire up the Python interpreter and try it out. Try it out identifying the user. In this try it out, you find out some information. 1. Start the OS module, as the name suggests, provides access to many operating system features. It is, in fact, a package with a submodule, os.path, that deals with managing file paths, names, and types. The OS module is supported by a number of other modules that you meet as you work through the various topics in this chapter. These myriad modules are collectively referred to as the OS modules, uppercase, and the actual OS module as OS, lowercase. If you are familiar with systems programming on a Unix system, or even with using a Unix shell such as Bash, many of these operations will be familiar to you. The OS is primarily there to manage access to the computer's hardware in the form of CPU, memory, storage, and networking. It regulates access to these resources and manages the creation, scheduling, and removal of processes. The OS module functions provide insight and control over these OS activities. In the next few sections, you look at these common tasks. Collecting user and system information. Managing processes. Determining file information. Manipulating files. Navigating folders. Note one of the biggest changes in Python version 3 is its increased focus on internationalization and recognition and use of Unicode. The OS module is no exception, and the functions accept Unicode strings. However, the underlying OS functions and file names are not necessarily Unicode aware, and Python will, in those cases, do a conversion to bytes using the system encoding found in sys.get file system encoding. This is not guaranteed to work in every case, so, very occasionally, a Unicode error may be raised. In those cases, you either have to convert the string into a more OS-friendly form before calling the function, or look for an alternative approach to solving your problem. 50 Chapter 2 Scripting with Python. 2. Type the following code into the interpreter. Import os.getlegend, agald os.getuid, hashtag not Windows 1001 import pwd hashtag not Windows pwd.getwid, os.getuid, hashtag not Windows pwd.struct underscore password, pw underscore name equals agald, pw underscore password equals unused, pw underscore uid equals 1001, pw underscore git equals 513, pw underscore geckos equals Alan Gald, udocumentation // agald, s1-5-21-2472883112-93377554227-21367237191, pw underscore dir equals /home/agald, pw underscore shell equals After importing the OS module in the FI-RST line, you got the login name as a string. That is generally most useful for creating personalized prompts or screen messages. Unfortunately, for Windows users, that's it. The rest of the try-it-out code is suitable for Unix-based systems only. However, all is not lost because you can also find some of this information from environment variables, which you look at a little later in the section obtaining information about the current process. If you have a Unix-based system, you use os.getuid to get the user ID as the OS sees it, namely a numeric value, which you can then use with various other functions. The next lines import and use functions from the password module, pwd, to translate the OS user ID into a more complete set of information that includes the real name, default shell, and home directory. This is obviously much more informative, but it requires the UID from os.getuid as a starting point. An alternative function, os.getpunum, takes the login name instead and returns the same information. Finally, you used pwd.getWall and a for loop to extract all of the usernames for this system. Next you find out what kind of permissions the users have on file they create. This is signify can't because it affects any file your code produces. It may be that you need to temporarily alter the permissions. For example, if you need to create a file that you execute later in the program, it needs to have execute privileges. In Unix, these settings are stored in something known as a mask or user mask. It is a bit mask, like the ones you used at the end of Chapter 1, where each bit represents a user access data point, as described next. Python lets you look at the amask value, even on Windows, using the os.amask function. The os.amask function has a slight quirk in its usage, however. It expects you to pass a new value to accessing the operating system 51. Now that you understand what you are trying to do, it's time to try it out. Try it out reading and modifying amask values. In this try it out, you read, modify, and restore the current user's amask value. To do so, follow these steps. 1. Start the Python interpreter. 2. Type the following code into the interpreter. Import os.amask 0b11111111 hashtag binary for all false 111x318 bin 18 0b10010 os.amask 18 511. The function, it then sets that value and returns the old value. But if you only want to find out the current value, you can't do it. Instead, you need to set the amask to a temporary new value, read the old one, and then reset the value to the original. The format of the mask is very compact, consisting of 3 groups of 3 bits, 1 group for each of owner, group, and world permissions, respectively. Note 3 bits can be concisely shown as an octal digit, and for that reason you will often find Unix documentation that expresses these values in octal. Python can use octal values, too, by representing the numbers with 00 in front, so that 00777 represents 9 bits, all set to 1. Table 2 to 1, Amask binary mappings. Amask binary value read, write, execute values 000 read equals true, write equals true, execute equals true 001 read equals true, write equals true, execute equals false 010 read equals true, write equals false, execute equals true 011 read equals true, write equals false, execute equals false 100 read equals false, write equals true, execute equals true 101 read equals false, write equals true, execute equals false 110 read equals false, write equals false, execute equals true 111 read equals false, write equals false, execute equals false. Within a group the 3 bits each represent one type of access, read, write, or execute. These are most conveniently written using explicit binary notation. Table 2 to 1 shows how each 3-bit binary value maps onto permissions. 52 Chapter 2 Scripting with Python. Another place to look for the system the user is running is in the sys module and, in particular, the sys.platform attribute. This attribute often returns slightly different information than that found using os.name. For example, Windows is reported as Win32 rather than NT or CE. On Unix, another function in OS called os.aname provides slightly more detail. If you have several different OSs available to you, it can be interesting to compare the results from these different techniques. It is recommended that you use the os.name option simply because it is universally available and returns a well-defined set of results. One other snippet of information that is often useful to collect is the size of the user's terminal in terms of its lines and columns. You can use this information to modify the display of messages from your scripts. The shootil module provides a function for this called shootil.get_terminal_size, and it is used like this. Import shootil calls, lines equals shootil.get_terminal_size, calls 80 lines 49. How it works. You started out by calling os.amask with a binary value of 11111111. That sets all permissions to false, which you did as a security feature in the event that something went wrong. It's better to have the mask too restrictive than leave the user vulnerable to security exploits. Python then printed the decimal value 18. By calling the bin function, you see that 18 has the binary mask value of 10,010. If you pad that with zeros to get the full 9-bit mask and split it into 3-bit groups, you see that it is 000010010. Referring back to table 2 to 1, you find that this value represents full access to the owner, but only read and execute access to group and world users. Finally, you restored the user's original setting by calling os.amask, again with an argument of 18, the original value returned by amask, and the previous mask value, 11111111, that you had set was printed, in decimal, as 511. Sometimes you want to know what kind of computer system the user is running, in particular the details of the OS itself. Python has several ways of doing this, but the one you look at Fiverr is the os.name property. At the time of writing, this property returns one of the following values, POSIX, NT, Mac, OS2, CE, or Java. Note the Java value is included, although not strictly in OS. For Java versions of Python, as opposed to the default C version, it is useful to know that you are running under a Java Virtual Machine, JVM. Accessing the operating system 53. The disadvantage of environment variables is that they are highly volatile. Users can create them and remove them. Applications can do likewise, so it is dangerous to rely on the existence of an environment variable. You should always have a default value that you can fall back on. Fortunately, some values are fairly reliable and usually present. 3 of these are particularly useful for Windows users because the pwd.getWid and os.uname functions discussed earlier are not available. These are home, OS, and processor_architecture. If you do try to access a variable that is not defined, you get the usual Python dictionary error. On most, but not all, operating systems, a program can set, or modify, environment variables. If this feature is supported for your OS, then Python reflects any changes to the os.environ dictionary back into the OS environment. In addition to using environment variables as a source of user information, it is quite common to use them to define any user specify C. Configuration details about a program, for example, the location of a database. This practice is slightly frowned upon nowadays, and it's considered better to use a configuration file for such details. But if you are working with older applications, you may need to refer to the environment for such things. If the terminal size cannot be ascertained, the default return value is 80 times 24. A different default can be specified as an optional argument, but 80 times 24 is usually a sensible option, because it's the traditional size for terminal emulators. Obtaining information about the current process. It can be useful for a program to know something about its current status and runtime environment. For example, you might want to know the process identity, or if the process has a preferred folder in which to write its data files or read configuration data. The OS modules provide functions for determining these values. One such source of process information is the process environment, as defined by environment variables. The OS module provides a dictionary called os.environ that holds all the environment variables for the current process. Note on older versions of Python, the underlying os.get_terminal_size must be used, but in version 3, the tuple version is recommended instead. Note the number of variables on any given system depends on all sorts of local considerations, including the number and nature of the applications installed, because many applications create their own environment values during installation. 54 Chapter 2 Scripting with Python. Try it out investigating the process environment. In this try it out, you investigate the process environment on your computer. Complete the following steps. 1. 2. Type the following. Import OS. How it works. After importing OS in the FI_RST line, the FI_RST thing you did was determine the current process ID. You are in the Python interpreter, so it is the interpreter process itself that you are identifying. The next line reads the parent process ID, in this case, that is the OS shell program. You can use these IDs when interacting with other operating system tools, as described in the next section. You then used the os.getCud function, which stands for Get Current Working Directory, to determine which directory is currently the default. This is usually the directory from which the interpreter was invoked, but, as you will see, it is possible to change directory within your program. os.getCud is a useful way of checking exactly where your code is working at any given time. Accessing the operating system 55. Next you found out how big your environment was by displaying the length of the os.environ dictionary. You then pulled out the value of the home environment variable that shows the user's home directory. You then tried to access a variable called testing123, but because it did not exist, you got a error. You attempted to create a testing123 variable by assigning the number 42, but that yielded a type error, because environment variables must be strings. You then assigned the string value 42 to the testing123 variable, and succeeded in creating a new environment variable for this process. Remember that the environment is local to this process, and any subprocesses that it spawns. This is not visible in other external processes. You next read the value again, and this time got a value with no error messages, confirming that you had succeeded. Finally, you deleted the variable and proved that it was gone by once more attempting to read it, resulting in, as expected, an error. Managing other programs. It is often useful to be able to run other programs from within a script, and the subprocess module is the preferred tool for this. The subprocess module contains a class called Popen that provides a very powerful and flexible interface to external programs. The module also has several convenience functions that you can use when a simpler approach is preferred. The documentation describes how to use all of these features. In this section you use only the simplest function, subprocess.call, and the Popen class. Note historically, Python has had several ways to run subprocesses. This has led to considerable confusion and a proliferation of options. Most of these mechanisms are still available so as not to break old code, but you are strongly advised to use the subprocess module discussed here for any new code you write. The most basic use of the subprocess module is to call an external OS command and simply allow it to run its course. The output is usually displayed on screen or stored in a data file somewhere. After the program completes, you can ask the user to make some kind of selection based on what was displayed, or you can access the data file directly from your code. You can force many OS tools, especially on Unix-based systems, into producing a data file as output by providing suitable command line options, or by using OS file redirection. This technique is a very powerful way to harness the power of OS utilities in a way that Python can use for further processing. This basic mechanism for calling a program is wrapped up in the subprocess.call function. This function has a list of strings as its phi-rst parameter, followed by several optional keyword parameters that are used to control the input and output locations, and a few other things. The easiest way to see how it works is to try it out. 56 Chapter 2 Scripting with Python. Try it out starting external programs. In this try it out, you call various programs from within Python. Complete the following steps to see how it works. 1. Create a test directory, called root, and populate it with a few text files. Either create them from scratch or copy them from somewhere else. It doesn't matter what they contain, you are only interested in their being there at this stage. To get the same results as shown here, the structure should look like this. Root filea.txt leb.txt. 2. Change into your root folder and start the Python interpreter. 3. Type the following code at the prompt, be sure to use the right commands for your OS. Import subprocesses sub.call ls hashtag not windows file a.txt file b.txt 0 sub.call ls stout equals open ls.txt w hashtag not windows 0 sub.call cmd /c dir /b hashtag windows only file a.txt file b.txt 0 sub.call cmd /c dir /b stout equals open ls.txt w hashtag windows only 0 sub.call more ls.txt hashtag not windows file a.txt file b.txt ls.txt 0 sub.call cmd /c type ls.txt hashtag windows only file a.txt file b.txt ls.txt 0 4 line in open ls.txt print line file a.txt file b.txt ls.txt. How it works. After importing subprocess with the alias sub in the phi-rst line, it just saves some typing later. You called sub.call for the phi-rst time with an argument of ls or cmd /c dir /b depending on your OS. Notice that dir is actually a subcommand of the command exe shell process. The Windows help system explains what the /c and /b flags do. The output is displayed on stout. You're accessing the operating system 57. One problem that can occur when running external programs is that the OS cannot find the command. You generally get an error message when this happens, and you need to explicitly provide the full path to the program file, assuming it does actually exist. Finally, consider how to stop a running process. For interactive programs, the simplest way is for the user to close the external program in the normal way or issuing an interrupt signal using Ctrl and C or Ctrl and Z, or whatever is the norm on the user's OS. But for non-interactive programs, you may need to intervene from the OS, usually by examining the list of running processes and explicitly terminating the errant process. Terminal, but the file names are not accessible from within Python. The only thing returned by call is the operating system return code, which tells you if the program completed successfully or not, but it does not help you interact with the data in any way. You then used sub.call a second time, but this time you redirected stout to a new file, ls.txt. Next you used the operating system tool more, or type on Windows, to display the file. The fact that ls.txt is a regular text file also means you can access the data by opening the file and processing it in the usual way using Python commands. In this case you simply looped over the lines and printed them, but you could have stored and used the data for some other purpose just as easily. It is worth noting that exposing a list of files in a text file like this is a potential security issue, and you should delete the file as soon as possible after processing it. Tip: note that it is possible to get the terminal session confused, especially when running processes in the background. The result is usually that the keyboard seems to stop responding, or it produces strange characters. If this happens, the simplest way to restore order is to kill off any errant processes using the OS tools. This is one of the hazards of running subprocesses from inside Python. The subprocess module does its best to protect you from these scenarios, but you may inadvertently get things messed up from time to time. Note on Windows, another useful tool is os.startFile. Instead of passing a command to the function, you pass a file name, and Windows uses its file association database to start the appropriate command. As an example, if you pass it a text file, it may start the notepad editor. A second optional parameter called operation specify what the called program should do with the file, the most common options being open, which is the default, or print. The specify operation must be one that is recognized by Windows for the file type. You can see these by right-clicking the file in Windows Explorer. However, only a subset of that list is associated with an external program. An invalid operation results in an OSERror exception being raised. If in doubt, use the Python interpreter to experiment with the options and find out which ones work. You have just seen how easy it is to use subprocess.call to start an external process. You now learn how the subprocess module gives you much more control over processes and, in particular, 58 Chapter 2 Scripting with Python. To access the output of the command being run, you can add a couple of extra features to the call, like so. lsout equals sub, popen, ls, star dot asterisk, shell equals true, stout equals sub dot pipe, dot stout for line in lsout. Print, line. Here you specify that stout should be a sub dot pipe, and then assign the stout attribute of the popen instance to lsout. A pipe is just a data connection to another process, in this case between. How it enables your program to interact with them while they are running, especially how to read the process output directly from your script. Managing subprocesses more effectively. You can use the popen class to create an instance of a process or command. Unfortunately, the documentation can appear rather daunting because the popen constructor has quite a few parameters. The good news is that nearly all of those parameters have useful default values and can be ignored in the simplest cases. Thus, to simply run an OS command from within a script, you only need to do this. Windows users should substitute the dir command from the previous example. Import subprocesses sub, popen, ls, star dot asterisk, shell equals true, subprocess, popen object at 0x7fd3 edec book tmp. Notice the shell equals true argument. This is necessary to get the command interpreted by the OS command processor, or shell. Doing so ensures that the wildcard characters, star dot asterisk, as well as any string quotes, and the like are all interpreted the way you expect. If you do not use the shell parameter, this happens. Sub, popen, ls, star dot asterisk, subprocess, popen object at 0x7fcd328cls, cannot access, no such file or directory. Without specifying shell equals true, the operating system tries to find a file with the literal name star dot asterisk, which doesn't exist. The problem with using shell equals true is that it also creates security issues in the form of a potential injection attack, so never use this if the commands are formulated from dynamically created strings, such as those read from a file or from a user. Note an injection attack is where a malicious, or very slapdash, user types an input string that is read and interpreted by your program, but, rather than containing harmless data, it contains potentially harmful commands, possibly resulting in deletion of files or worse. The shlex module contains a quote function that can mitigate the risks, but care should still be exercised when running dynamically generated strings. Accessing the operating system 59. Your program and the command that you are executing. Having done so, you can then treat the lsout variable just like a normal Python file and read from it, and so on. You can send data into the process in much the same way by specifying that stin is a pipe to which you can then write. The valid values that you can assign to the various streams include open files, file descriptors, or other streams, so that str can be made to appear on stout, for example. Note that it's possible to chain external commands together by setting, for example, the input of the second program to be the output of the first. That produces a similar effect to using the OS pipe character on a command line. Try it out using subprocess, popen to access stin/stout. To see how to use subprocess, popen to interact with processes, complete the following steps. 1. Start the Python interpreter in your root folder. 2. Type this code. Import subprocesses sub, popen, ls, #Windows use, cmd/cdir/b, subprocess, popen object at 0x7fd3 eecc file a.txt file b.txt ls.txt #Windows use, cmd/cdir/b, stout equals sub.pipe, ls equals sub, popen, ls, stout equals sub.pipe, for f in ls.stout, print, f. bfile.txt \n bfileb.txt \n bls.txt \n x equals sub, popen, x, test.txt, stin equals sub.pipe, #not windows ex stin.write, bi \enthus is a test \n, #not windows 19 ex stin.write, bwq \n, #not windows 31 plus stopped python 3 sub, popen, non-existent file, traceback, most recent call last file stin, line 1, in module file /usr/lib/python 3.2/subprocess.py, line 745, in __init_restore signals, start _new _session, file /usr/lib/ Python 3.2/subprocess.py, line 1361, in _execute_child raise child _exception _type, erno_number, error _message, ozerer, erno2, no such file or directory, non-existent file. How it works. To start, you imported subprocess with the alias sub. The first couple of commands just duplicated what you did with subprocess.call, in that you initially produced a file listing on Stout, but again could not use that data. The second case is more interesting because you redirected Stout to a sub.pipe that allowed you to read it via the Stout attribute. Notice the difference between the Stout parameter, which you set to sub.pipe within the Popen constructor call, and the Stout attribute that you use for reading data from the Popen instance and is accessed via dot notation. To use this, you also 60 Chapter 2 Scripting with Python. Assigned the result of the Popen call to a variable called ls. Popen is actually a class, and the result of the call is a new Popen object instance. The end result is very similar to the subprocess.call case where you fed the output to a file ls.txt, and then read the file, but in this case you don't wind up creating any files. Rather, you read directly from the process. This means you don't end up cluttering your file system with little temporary files that have to be tidied up afterwards. The next example used the Unix line editor X, but this time you redirected stin to sub.pipe, and then fed some commands into the editor to create a short text file. You also passed in a file name as an argument by providing a second string in the rst argument to Popen. Note that the input to stin must be a byte string, bxxxx, rather than a normal text string. The penultimate example shows what happens if you try to open a non-existent file, or don't provide the correct path information. You get an error exception that you could, of course, catch using Python's try/except structure. In the try it out examples, you accessed stin and Stout directly, however, this can sometimes cause problems, especially when running processes concurrently or within threads, leading to pipes filling and blocking the process. To avoid these issues, it's recommended that you use the Popen.communicate method and index the appropriate stream. This is slightly more complex to use, but avoids the problems just mentioned. Popen.communicate takes an input string, equivalent to stin, and returns a tuple with the rst element being the content of Stout, and the second the content of str. So, repeating the file listing example using Popen.communicate looks like this. ls equals sub, Popen, ls, Stout equals sub.pipe, lsout equals ls.communicate, 0, print, lsout, bfile.txt /fileb.txt /nls.txt /n. To conclude this section, it is worth pointing out that, for simplicity, you have been using fairly basic commands, such as ls, in the examples. Many of these commands can be performed equivalently from within Python itself, as you see shortly. The real value in mechanisms like subprocess.call and Popen is in running much more complex programs such as file conversion utilities and image processing batch tools. Writing the equivalent functionality of these tools in Python would be a major project, so calling the external program is a more sensible alternative. You use Python where it is strongest, in orchestrating and validating the inputs and outputs, but leave the heavy lifting to the more specialized applications. Obtaining information about files and devices. The OS module is heavily biased to the Unix way of doing things. As such, it treats devices and files similarly. So finding out about devices, such as the current terminal session, looks a lot like finding out about files. In this section you now look at how you can determine file status and permissions, and even how to change some of their properties from within your programs. Consider the following code. Import os.lister. Accessing the operating system 61. File.txt, fileb.txt, ls.txt, test.txt, os.stat, file.txt, POSIX.stat_result, st_mode equals 33204, st_eno equals 1125899907117103, st_dev equals 14915196554, st_link equals 1, st_uid equals 1001, st_git equals 513, st_size equals 257, st_time equals 13886766837, st_time equals 13886777418, st_time equals 13886777418. Here you check the current directory, listing with os.lister. Now that you've seen os.lister, you hopefully realize that your use of ls or dir in subprocess was rather artificial, because os.lister does the same job directly from Python, and does it more efficiently. You then used the os.stat function to get some information about one of the files. This function returns a named tuple object that contains 10 items of interest. Perhaps the most useful of these are st_uid, st_size, and st_time. These values represent the file owner's user ID, the size, and the last modify cation date time. The times are integers that must be decoded using the time module, like so. Import time.localtime, 13886777418, time.struct_time, tm_year equals 2014, tm_mon equals 1, tm_day equals 2, tm_hour equals 15, tm_min equals 43, tm_sec equals 38, tm_wday equals 3, tm_ida equals 2, tm_ist equals 0, time.strf time, %y%m%d, time.local time, 138-867-7418, January 2nd, 2014. Here you used the time module's local time function to convert the integer st_m time value into a time tuple showing the local time values, and from there into a readable date string using the time.strf time function with a suitable format string. You look more closely at the time module in the using the time module section later in this chapter. The simple 10 value tuple returned from os.stat is generally convenient, but more details are available via os.stat than the tuple provides directly. Some of these additional values are OS dependent, such as the st_ob type attribute found on Risco systems. You need to do a little bit more work to dig these out. You can access the details by using object attribute notation. Perhaps the most interesting phi-eld that you can access from os.stat is the st_mode value, which tells you about the access permissions of the file. You use it like this. Import os_stats equals os.stat, file.txt, stats.st_mode 33204. But that's not too helpful, it's just an apparently random number. The secret lies in the individual bits making up the number, it's another bit mask. You may recall the amask bit mask that you looked at earlier in the chapter. The st_mode is conceptually similar to the amask, but with the bit meanings reversed. You can see how the access details are encoded by looking at the last 9 bits, like this. Bin, stats.st_mode, 911111101. By using the bin function in combination with a slice, you have extracted the binary representation of the last 9 bits. Looking at those as 3 groups of 3, you can see the read/write/execute values for owner, group, and world respectively. Thus, in this example, owner and group have all 3 bits set to 1, true, but world only has the read and execute bits set to 1. 62 Chapter 2 Scripting with Python. True, and the write access is 0, false. Note that these are the direct inverse of the meanings of the amask bits, do not confuse the two. The higher order bits also have meanings, and the stat module contains a set of bit masks that can be used to extract the details on a bit-by-bit basis. For most purposes the preceding access bits are sufficient, and helper functions exist in the os.path module that enable you to access that information. You'll revisit this theme when you look at os.path later in the chapter. You have several other ways to determine access rights to a file in Python. In particular, the OS module provides a convenience function, os.access, that takes a file name and flag variable, one of os.f_ok, os.r_ok, os.w_ok, or os.x_ok, that returns a Boolean result depending on whether the file exists, or is readable, writable, or executable, respectively. These functions are all easier to use than the underlying os.stat and bitmask approach, but it's useful to know where the functions are getting their data. Finally, the OS documentation points out a potential issue when checking for access before opening a file. There is a very short period between the two operations when the file could change either its access level or its content. So, as is usual in Python, it's better to use try/except to open the file and deal with failure if it happens. You can then use the access checks to determine the cause of failure if necessary. The recommended pattern looks like this. Try, myfile equals open, myfile.txt. Except permission error, #test/modify the permissions here else, #process the file here finally, #close the file here. Having seen how to explore the properties of individual files, you now look at the mechanisms available for traversing the file system, reading folders, copying, moving, and deleting files, and so on. Navigating and manipulating the file system. Python provides built-in functions for opening, reading, and writing individual files. The OS module adds functions to manipulate files as complete entities. For example, renaming, deleting, and creating links are all catered for. However, the OS module itself provides only half of the story when it comes to working with files. You look at the other half when you explore the util module and other utility modules that work alongside OS. Note in Python 3.4 a new module was introduced called pathlib, which aims to provide an object-oriented view of the file system. This potentially replaces much of that functionality discussed in this section. However, pathlib is marked as provisional, which means that the interfaces could change significantly in future releases, or the module could even be removed from the library. Because of this uncertainty, pathlib is not used here. Accessing the operating system 63. You start with reading and navigating the file system. You've already seen how you can use os.lister to get a directory listing and os.getcode to tell you the name of the current working directory. You can use os.mdir to create a new directory and os.str to navigate into a different directory. Try it out accessing directories in Python. In this try it out, you create and access directories using Python. Complete the following steps. 1. Change into the root directory you used previously. 2. Start the Python interpreter and type the following Python commands. Import os_cwd equals os.getcode, print, cwd, /home/agald/book/root os.lister, cwd, file.a.txt, file.b.txt, ls.txt, os.mdir, subdir, os.lister, cwd, file. How it works. After importing os in the file.rst line, you stored the current directory in cwd, and then printed it to conf.rm that you were where you thought you were. You then listed its contents. Next, you created a folder called subdir and changed into that folder. You verified the move succeeded by calling os.getcode, again from the new folder, and found that the folder had indeed changed. Finally, you changed back up to the previous directory using the shortcut, and once again verified that it worked with os.getcode. One problem with the os.mdir function used here is that it can only create a directory in an existing directory. If you try creating a directory in a place that doesn't exist, it fails. Python provides an alternative function called os.makers, note the difference in spelling, that creates all the intermediate folders in a path if they do not already exist. You can see how that works with the following commands. os.mdir, test2/netester, traceback, most recent call last file stin, line 1, in module oserer, erno2, no such file or directory, test2/netester os.makers, test2/netester, os.str, test2/netester, print, os.getcode, /home/agald/book/root /test2/netester. 64 Chapter 2 Scripting with Python. Here the original OS